Parametric functions, day 2, slope and concavity. All right, here are the parametric functions, and here is y equal f of x, y, and x. We can, again, substitute x into here. So we're going to substitute x, and then we're going to substitute y with its parametric form here. And we're going to use the chain rule. So g prime of t is equal to the derivative of the outer with respect to the inner times the derivative of the inner. Now we're going to, and that represents f prime of x, because this is an x. We're going to isolate that. F prime of x is g prime of t over f prime of t. And in fraction form, in the derivative of fractions, it looks something like this. Okay, so here's the derivative rule for parametric form. If you think of this as a slope, dy over dt, and this is a slope, dx over dt, you can see that this does simplify to dy over dx. So hopefully the math kind of makes sense to you. Now, the second derivative, let's be careful about that. That's the derivative of the first derivative. And since it's in parametric form, you're going to take the derivative with respect to t of the function, which is right here, divided by dx dt. Please do not make this mistake right here. All right, we want to consider the curve, and we want to sketch a graph of the curve, so we can go ahead, I've shown you how to use a calculator to graph that. We want to find the highest point, so that's the max value. Okay, so the max value requires that we find a first derivative. Okay, then it asks us for the points of inflection on the curve in this interval, and points of inflection is going to require a second derivative. So let's go to the next and let's go ahead and find the derivative dy dt, dx dt we're getting here. We're trying to find the highest point, which means we're looking for when dy dx is equal to 0. So right over here, dx equals 0. Okay, well that's going to happen when the numerator is 0. So cosine of t equal to 0. So within our within the values for t, that's going to be at pi halves. And if you put pi halves in here and in here, you're going to get where this happens, what's the highest point. And that's going to be at the point, it's going to be a decimal, negative 2.533, 2. All right, now we're being asked for the points of inflection, which means I have to find the derivative. So I'm going to find the derivative of this right here, which is going to require the quotient rule, and then dx dt, and dx dt we already have as up 2t. We're going to simplify. We want to find the points of inflection, and the points of inflection mean where the derivative changes from positive, negative, or negative to positive. So let's take a look at when this is equal to 0. When it's equal to 0 on a graph, it's going to be right here. And you can see that the second derivative is negative before that and positive before that. So that is a point of inflection. And this point, this particular point, ends up being 2.831. And the y ends up being 0.673. Okay, the arc length of a parametrized curve. Now this is our, these are curves where when it was in terms of x or in terms of y. In terms of t, it's going to look like this. And remember, it's that same idea that this is the hypotenuse of a Pythagorean theorem. And so we're going to write dx dt, dy dt with dt here. Okay, we are going to be measuring the length of this asteroid. And what we're going to do is we're going to find this length right here, and then we're going to times it by 4 so that we can get the length of all of the sides. So we're going to find the derivative of dx dt, and remember the formula that we had before that. We need to have a squared here and squared here. So this is going to be the derivative of dx dt is 3 cosine squared t times negative sine t quantity squared. And then this one will be 3 sine of t times, 3t squared times the cosine of t quantity squared. And so these quantities are going to be put into here, do some simplifying, and we're going to find a factor that's going to be equal to 1, and so we're going to be given this. So we're going to go from when x is 0, that's going to happen at t equal to 0, and then put a 0 here. We're going to get a 1. So this is 0, 1. This is 1, 0. And this is going to happen from 0 to pi halves. Remember, a fourth of the way through the values for t. And we're going to find this value, and this value is going to be 3 halves. But remember, we've only found this portion here. So the total length of the asteroid will be 4 times 3 halves, which is going to be equal to 6. Okay, surface area, how's that going to change? Remember, this is the arc length part, and then this is the 2 pi r. Remember, this is the height of the radius of the strips that are going around. Okay, how about area? We can find the area under parametrized curves, and we do that by what we were doing before, height times the width. This is what we did last year. So we would find little rectangles underneath the curve, and we would add them together. All right, well, what is y in our parametrized? Well, it's right here. This is what y is. And then we have to find dx. That means I have to find the derivative of x with respect to t here. And so here's a form of what we're going to do that. Now, this is a cycloid. Cycloids, let me tell you, suppose that a wheel rolls along the horizontal line. So if you follow the point along the wheel and trace it, you're going to get what we call a cycloid. So what we're going to do is find the area under the one arch of a cycloid. And this happens to be, they're not giving us specific radius, but it's a radius, and that's a constant. And we want to figure out all the areas, and we're going to do that with rectangles. And we're going to, this is our height, and here's our width. And we're going to go from 0 to 2 pi r. And our y, here it is. We're going to write it right there. And then dx, that means we're going to take the derivative here, and that's going to be right here. Do some multiplying out. We're going to take our r squared out here because it's a constant. And we're going to, this is interesting. This identity has to be changed. So cosine squared theta is going to have have an identity, replace it 1/2. This is the half angle, or double angle formulas, I should say. So we're going to replace it with that. Why? Because we can't deal with the square. We need to take the square and write it in terms of something that's not squared. And then we integrate, and we're going to get this answer. Okay, here's the examples from the handout that I've given you. And so you need to be able to find the derivative and the second derivative. And a lot of times it's good just to find the derivative of y with respect to t and x separately, and then go ahead and put them into the quotient. Now, to find the second derivative, remember that we're going to find the derivative of this. So that's what's taking place here. And don't forget to divide it by dx dt, and dx dt is right here. In this particular problem here, I'm being asked to find the equation of the tangent line, which again requires that we find the derivative, which is this, evaluate the derivative at 3 pi fourths, and that slope is here, and then just evaluate t into x into y, so that we find our, oh, that's our x and that's our y. This is our slope, sorry about that. And then we go ahead and put it in point slope form. Okay, in this example, we want to find the horizontal and vertical tangencies. So we figure out the derivative, and the yellow part is going to help us figure out our horizontal tangents. We set that part equal to 0, and that's going to happen at t equal to 3 halves. We put 3 halves into x and y, we'll get the location where this occurs. Okay, vertical tangents are when the denominator is equal to 0, or when it's undefined. We set that equal to 0, we find what t is equal to. Substituting t equal to 1/2 into both x and y, we'll get the point at which that occurs. And here's our last one, and this is arc length. And again, finding the derivatives of x and y will allow you to put it into the formula. So here it is, dx dt, dy dt. Square those, put them in here, integrate. Again, it's telling you where to integrate from 0 to 1. And that's the end of the screencast.